And welcome back for section 2.4. Section 2.4 is all about continuity. It's a really important idea when it comes to calculus because there's sometimes we can do things with continuity, sometimes there's not. So the first thing I want to do is let's look over this first couple of paragraphs here. So many functions have the property that their graphs can be traced with a pencil without lifting the pencil from the page. Such functions are called continuous. So guys, a really mathematically thinking way of doing this. If you can draw the graph without picking your pencil up, that graph is considered continuous. So other functions have points at which the break in the graph occurs that satisfy this property over intervals contained in their domains. They are continuous on those intervals and are said to have a discontinuity to point where a break occurs. So sometimes they can be continuous over their particular intervals, but then you have a break in the actual graph. So we're going to look at all different types of this stuff today. So I want to continue over to, let's look at the definition here. So the definition, a function f of x is continuous at a point A if and only if the three conditions are satisfied. F of A is defined. The limit as x approaches A of f of x exists. And the limit as x approaches A of f of x equals f of A. So the value that you're approaching, if you plug it in through direct substitution, that's what they're talking about. So a function is discontinuous at a point A if it fails to be continuous at A. Okay, woohoo, that makes sense, right? If it's not continuous, it's got to be discontinuous. It's kind of weird to put that way, but there we go. Let's talk about the problem-solving strategy for this. So you're going to check to see if f of A is defined. If f of A is undefined, we need to go no further. This function is not continuous. Now, guys, one of the things I want to point out here, this is the algebraic way of doing it, right? If we were looking at a graph, we would just look and say, oh, yay, it's been graphed. We do have to kind of pay attention to holes, though. We've talked about holes previously. Remember, if you're using something like Desmos, they don't show holes, but there may be one in there. Number 2, compute the limit as x approaches A of f of x. In some cases, we may need to do this by first computing the limit from the left, limit from the right, and seeing if they're equal. If the limit as x approaches A of f of x does not exist, that is, it's not a real number, then the function is not continuous at A and the problem is solved. If a limit as x approaches A of f of x exists, then we're going to continue on to step 3, and that's where we do our direct substitution here, f of A and limit as x approaches f of x. If they're not equal to each other, then the function is not continuous. So the book's going to go into some examples, and I think I want to go over these examples. So here is the continuity to point condition 1. So notice condition 1 is that f of A is defined. So they're giving us the function f of x equals x squared minus 4 over x minus 2. And we want to determine, is it continuous at x equals 2? So if we go through and plug 2 in, we already see that this one's going to be undefined at f of 2 because that's actually a hole. We've done a problem. We may have actually done this very problem in a previous example. So it actually turns out it's discontinuous. Of course, if we graph it, we do see that there's a hole there at 2. So it's discontinuous at f of 2. All right, let's look at a different example. Here is, we're going to look at condition 2. So going back up to condition 2, that was the limit has to exist. In other words, as we approach from both sides, we get the same thing. And of course, we've got a piecewise defined function for this example. So f of x equals negative x squared plus 4 as long as x is less than or equal to 3, and then 4x minus 8 if x is greater than 3. So they're going to go through and find the limit at 3. First, they make sure that there's even a value at 3. So what they're going to do is they're going to plug 3 into the top equation because that's the one that includes 3 as part of its domain. And as long as you have a value of 3, so that's defined, which is the reason we had to stop in the previous example, then we can continue on to the second condition. And of course, if we plug 3 in, it does end up being defined. We get negative 5. So now we're going to calculate the limit as x approaches 3 of f of x. So we're going to do it from the left and right. if I'm coming from the left, I'm going to use this equation. If I'm coming from the right, I'm going to use this equation. So that's what you're seeing them doing here. So they go in, they take the limit, they plug 3 in, they get -5, they get +4. Those two things are not the same value. So if those two things are not the same value, the limit does not exist, and therefore it is not continuous. You know, we can also graph it, and this is what the graph looks like. Yeah. So this part's fine, right? And this part's fine, but because they're both part of our problem, I do have to pick up my pencil to be able to draw the second part here. And then finally, we're looking at condition 3. Remember, you only have to worry about condition 3, which is the limit as x approaches a of f of x equals f of a, if it passes these other two conditions. So let's look at that. So we've got another piecewise defined function where we've got sine of x over x if x is not equal to 0, and then 1 if x is equal to 0. So it looks like we're filling in something here. So if we plug 0 in, we know it's got to be 1, right? So it is going to be defined because they've went through and actually defined it for that. So now we're going to take the limit. So if we were to take the limit from the left and from the right, this thing is going to end up being 1, which is good. And now we're going to compare what it should be, right, when I plug in 1 to what we actually get. So if we plug in, excuse me, not 1, when we plug in 0. So when I plug in 0, we got 1 from the original equation. Here, when we took the limit, we got 1. So what does that mean? All three conditions are met. That means that this thing is going to be continuous at x equals 0. So that's how you find continuity algebraically. Okay. So we've went over this. Next thing I want to do before we actually get into any type of problem solving is let's talk about the types of discontinuities. So the types of discontinuities that we are going to look at. We classify the types of discontinuities we have seen thus far as removable discontinuities, infinite discontinuities, or jump discontinuities. Intuitively, a removable discontinuity is a discontinuity for which there is a hole in the graph, right? So this is an example of a removable discontinuity. We have a jump discontinuity, which means it literally jumps. The ends don't meet up there. Then we have an infinite discontinuity where your function shoots off to positive infinity or negative infinity. Although these terms provide a handy way of describing 3 common types of discontinuities, keep in mind that not all discontinuities fit neatly into these categories. Of course not, it's math. And so here's going to be the actual algebraic definitions for this. F has a removable discontinuity at A if the limit as x approaches A of f of x exists. F has a jump discontinuity at A if the limit as x approaches A to the -1 of f of x. So if we're coming from the left, you're coming from the right, taking the limit. They both exist, but they're not the same thing. And then finally, number 3, F has an infinite discontinuity if you take the limit as x approaches A from the left or x approaches A from the right, and it shoots off in one direction or the other. Cool. So that's our type of discontinuities. Let's do a couple of examples here. Oh, is there one more box I need to see? Let me check here. Nope, I think we covered that. All right. So let's look at example number 131. So for the following exercises, determine the points, if any, at which each function is discontinuous. Classify the discontinuity as jump, removable, infinite, or other. Okay. So with 131, we have f of x equals 1 over the square root of x. Now, I know what you're thinking. You're thinking, oh, this one's going to be, you're going to have an asymptote, and that is correct. However, if you think about the domain or what's allowed in this particular function, you have to be greater than 0. So 0 can't be included because it's in the denominator. You have to be greater than 0. So because your domain is x has got to be greater than 0. So let me make a note here. Where's my annotating? It's on number 131. Your domain, x has to be greater than 0. Because that's the case, the function is only going to be defined for the interval 0 to infinity. So we're going to be defined from 0 to infinity. And that's just because of the way the function's set up. So because that's where we're defined, this 1 over the square root of x, the only issue I would have had would have been 0. That's where I would have gotten the undefined. That's where I would have had the asymptote. But because the domain has to be greater than 0, this is going to be continuous all the way across the board. So this one is continuous. I know, it's really weird. We can actually go in and graph it right quick. 1 over the square root of x squared. Oh, this is cool. I haven't showed you guys how to do a square root yet. You can also type SQRT. That'll do a square root, but I've got my little thing here. What was this? X. So please notice here, should have cleared my page. This thing is only defined from 0 to infinity. Nothing past 0 is going to exist, and this thing is not going to touch 0. So over the course of this graph, if I was to draw it, I don't have to lift my pencil in a single place to be able to draw this graph. So it is continuous. A little bit harder to say algebraically. All right, so that's 131. What else can we do here? Let's look at, let's do 135. So 135, we have f of x equals 5 over e to the x minus 2. Now, because you've got an e to the x, this one doesn't have the issue that I had with the previous one. I can be positives or negatives with this one. So I'm really concerned with the fact that we do have that e to the x minus 2 on the bottom. So I would like to see where that e to the x minus 2 is going to go to 0. So I'm going to pull out e to the x minus 2, and I'm actually going to set it equal to 0. And when I set it equal to 0, this is going to tell me what's going to make it 0. So to go through and work this, in case it's been a little while, I'm going to add 2 to both sides. So we got e to the x equals 2. Now, please remember that if you are trying to pull an exponent off of something, you have to use logarithms or natural logarithms. I'm going to use natural logarithms because natural logarithms are what work with e's. So I'm going to take the natural log of both sides. So here, this x pulls out front. The natural log of e ends up being 1. So we've got x equals, or 1x equals, the natural log of 2. So that's the one value that x cannot be. So what this means is that something weird is happening at the natural log of 2. I could go through and actually take the limit as x approaches natural log of 2 from the left and from the right, but I'm going to do something a little bit different. I'm going to go to Desmos and actually see what's happening here. So just remember, natural log of 2 is where something weird's happening. So we have so unlike last time where I had this situation where I only had one graph right and it did this, that is not the case here. So we do have this thing flipping in 2 places. Let's see here. Let me do a table right quick. So I'm going to add me a little table here because I want to see what's the ln of 2 going to be. This needs to be f of x1, doesn't it? And there you have it. If we look at the natural log of 2, that's where we actually have this thing splitting. So that's why we're getting an undefined. So this is going to be an infinite discontinuity at x equals ln of 2. So we do have an infinite discontinuity at ln of 2. Cool. I am really liking Desmos. It takes me forever to type stuff in, but I like it. So let's go on and let's look at number 136. So same thing. We are asked to figure out if this thing has, you know, a hole, a jump discontinuity, whatever. So with this particular one, I am concerned about the x minus 2 on the bottom. The x minus 2 on top is fine, but I am worried about the x minus 2 on the bottom because I know, according to this, that we can't have x equal to positive 2. Because if I do, I've got an asymptote. So I do think that this thing is split. Let's talk about what happens, though, with it being split. A lot of times, guys, we like to think that, oh, if it's split, that must mean that we are approaching infinity or negative infinity, and that's not always the case. So what I'm going to do is I'm going to see what the limit's going to be from the left to right. So I'm going to go back in and let's actually graph this. So let's do f of x equals, then where's an absolute value? Oh, look, that make it easy for me. Absolute value of x minus 2. Now we can close our absolute value here. Divided by x minus 2. So what does this one do? So here's 2, right? There's 2. I've already got it wrote out here. X can't be 2. So yeah, this one has an asymptote, but this asymptote does something weird. Instead of shooting the graph off to negative infinity and positive infinity, this one actually causes a jump discontinuity. So this is an example of a jump discontinuity. So we do have a jump discontinuity to x equals 2. Okay. Guys, I think I'll stop the video there. We'll pick up again with another video, so I'll see you shortly.